Okay, merry-go-round has a radius of 1.8 meters and a moment of inertia of 197 kilogram meter squared. Oops. So here's the merry-go-round. I is 197. The radius is 1.8. Okay, a boy of mass 56 kilograms runs tangent to the rim. Okay. And he has 56 kilograms and he's moving at 3.2 meters per second and jumps on. Okay. The merry-go-round is initially at rest. What is the angular velocity after the boy jumps on? Okay. So this is a situation where we're still conserving the angular momentum. Okay. But this guy running in, right, he's like that point particle like we saw earlier, where he has an angular momentum about this center, right? Even though he's not rotating, but since he's moving at some radius to this center, he's going to have an angular momentum, okay? So initially, it's going to be mvr, right, of the boy, okay? And then after, he's going to be on the merry-go-round, right? So then it's just going to be I omega of the merry-go-round, right? Because he's no longer moving tangent to it because he's going to jump onto it, okay? All right, so let's see what else we need to do. What are we trying to find? The angular velocity. Okay, so we're going to have the angular velocity is going to be m boy v boy radius, okay, over I of that merry-go-round, all right? So we know the mass of the boy, and we know the velocity of the boy, okay, and we know the radius of the merry-go-round, right? Because it doesn't matter that he's out here, right? He's still that radial distance away, okay? Now all we have to do is find the rotational inertia of this merry-go-round, okay? So let's see. I'm assuming they're going to want us to do the merry-go-round as a disk, right? Okay, which is going to be 1/2 mr squared, okay? But right, you also now have this point particle boy sitting on the end, so he's going to give another mr squared, right? Because he's now sitting at that edge, okay? So it's going to be 1/2 mass of the oh, we don't even have to do that, stupid. I should read the problem. Okay, actually, we don't even need that because they're just giving us this value, okay? So that must be the 1/2 mr squared, okay? So 197 is the merry-go-round, okay, plus the boy, we still have to add the 56 kilograms of the boy times the radius squared, right? Because I still have to add that mr squared onto that, okay? All right, and let's hope that this comes out right because I have the answer, assuming the answer's right. Let's hope and pray that I don't have to do this over. Okay, divided by 197 plus 56 times 1.8 squared. 181.44. Okay, so 322.56 divided by 197 plus 181.44. Please, 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 please. Oh, hallelujah. 0.852 radians per second. All right, that was the answer, I think. Okay? All right. So when you're doing conservation of momentum, just keep in mind, right, it might be I omega, but it also might be this MRV. Or MVR, if it's a point particle sort of coming in, usually like tangent to a hoop or something is usually how it works. Okay, so you can use either one and you can mix and match those.